This is the setup for what's called an Atwood machine. And it consists of a few things. I'm going to pick up the camera here, don't get dizzy. Pulley up at the top with a string run around it. And the string is attached to these two bricks, and the masses are shown on the bricks. The two bricks are suspended above the floor. Now you may wonder why the bricks aren't moving if one mass is bigger than the other. That's not the mass right now. I'm going to add a small amount, a small brick to the one on the right to make its mass 0.65. At this point in time, both bricks have a mass of 0.55, but that will be their masses when the experiment starts. And the bricks are suspended above the floor. The distance from the bottom of the brick to the floor is written here, 0.675 meters. I'm going to add 0.1 kilograms to the right-hand brick so that now these masses are correct. I'm going to remove them. And I will let it fall as I time it. I suggest that you time it and see what you get and use your time, but I'm going to time it as well, and I'll show you what I get, because timing through the computer does not always work correctly. So I'm going to start the clock as soon as I release it and stop it when the larger brick hits the floor. Right? And I have that, 1.26 seconds. This is the lab on air resistance, and our falling object will be a coffee filter, because these fall very slowly. They have a big ratio of air resistance force to gravity force. So they reach terminal velocity very quickly within about 1 foot drop. And I will hold the coffee filter up high so when it comes into your field of view, it will already be moving at terminal velocity. We could prove that with our motion detector or even with a meter stick and a stopwatch, but we'll assume we've proven that. Your job in this lab is to figure out whether the airflow around a coffee filter is smooth, that is laminar flow, or rough, that is turbulent flow. And you can't just guess or use common sense. You have to show it mathematically. The procedure is that I will time one coffee filter as it falls from the tabletop level to the floor. Then I will nest a second one inside it, like this. So what does that do? What have I changed? Well, I've doubled the mass, but I've kept the area pretty much the same. So the K, the coefficient for air resistance, stays roughly the same, but I've doubled the mass. And I do the same thing. I measure the time from when it passes the tabletop until it hits the floor. That entire motion should be at constant terminal velocity. Now notice what you don't get in this lab. You never get the actual height that the object falls from the tabletop to the floor as a measurement. All you know is it's the same in both cases. You don't actually get the area or the value of K. You just know it's the same in both cases. I never actually tell you the mass of the coffee filter. I just tell you that I double it. And the one number that we do measure is time with a stopwatch, so you'll have two values for time. Those are your only two numbers in the entire lab. And from those two numbers, you have to prove whether the flow is laminar or turbulent. All right, so let's do this. Here's one coffee filter. The time is 0.73. Now I put a second coffee filter in it, doubling the mass but keeping everything else the same. And the time is 0.53. This is the part of the lab with the friction-free ramp. We use an air track, so it's virtually friction-free. The only thing you really get is that the length that this little car travels is 1.2 meters. You do not get the mass of the car. You can use a stopwatch, your timer, whatever works for you to time from when I release this from rest until it hits the end and has traveled the 1.2 meters. And I will give you a little countdown, like 3, 2, 1, go, like that. So you can time from when it leaves here to when it hits the end. And from that information, I want you to figure out what the angle is of this ramp, what the theta is, how much this ramp, the angle this ramp here makes with the horizontal. Just as in the notes in the homework, that angle theta. All right, it's going to get a little noisy because I'm going to turn on the blower. Okay, so 3, 3, 2, 1, go. This is for the friction part of the lab, but it's for the lab with angles. In ninth grade, you calculated the coefficient of friction between a book and the tabletop by pulling the book horizontally. And in that case, the friction force exactly equaled the pulling force, and the normal force exactly equaled the gravity force. Well, we're going to make this a little more difficult by pulling at an angle. Now, it's just a conceptual lab. We don't worry too much about exact measurements in AP Physics C, not in our labs. I want you to understand things, not to worry about the best possible accurate experimental technique to get your measurements. So we're going to say that this angle is 30 degrees with the vertical. I'm estimating, and we're not going to use a protractor. So we're going to say this angle is 30 degrees with the vertical. I'm going to pull it like this. Okay, so you're only allowed to make 2 measurements to figure out the coefficient of friction. One is to hold the book like this from the force meter, and you read about, we'll call that 17 newtons when the book is hanging stationary from the force meter. Then the second measurement we'll make is we'll put this at a 30-degree angle. Let's see, that would be 45. So I can even estimate 30 degrees. Like this height has to be half of the hypotenuse, right? The sine of 30 is a half, so that looks pretty close. Right, and I'll pull it along, and we'll round this to 4. So I get 4 newtons when I pull at a 30-degree angle to keep the book moving at a constant velocity.